Let's continue now with some properties of carboxylic acids and their preparation and the most common reaction that they give. Why are carboxylic acids more acidic than other organic compounds? The simplest question for this is that the carboxylic acids, for example, if you react that with a base, it forms a carboxylate anion that is soluble in water and has higher stability due to the resonance structures. As you see, this negatively charged can move from here to here. And due to the more resonance structures, more stabilized the carboxylate anion, the more possibility to dissociate and to give a higher acidity. Let's take a look, for example, when you compare with propanol, for example, with phenol and carboxylic acid, and also compared with hydrochloric acid. Of course, is not comparable because these are weak acids. But compared to propanol, compared to ethanol and phenol, ethanol and phenol itself has 1 million times difference due to the fact that the phenol is capable of forming resonance structures. In this case, compared to phenol, this is even stronger acid, but not compared to hydrochloric acid. Uncomparable, okay? What are the factors that increase or decrease acidity of carboxylic acids? The simplest answer is that electron withdrawing groups increase acidity of carboxylic compounds. Let's take a look, for example, at acetic acid and this trifluoroacetic acid. The problem here, the idea here is that the electronegative elements help to delocalize the negative charge, so stabilizing the anion. And let's move further to something else. In case you have in the aromatic rings, in case you have the groups that donate electrons, is going to decrease acidity, so it's going to destabilize the anion. In case you have electron withdrawing groups or deactivating groups, it's going to increase the acidity if you have to rank, for example. Okay, let's move now to the preparation of carboxylic acids. From alkyl benzene oxidation, it can have more than like CH2, CH3, at the end it's going to give only benzoic acid. It works best for primary and secondary, but not with tertiary carbons. So the product here is going to be benzoic acid, right? With potassium permanganate. Let's move to the second one, from oxidation of primary alkyls and aldehydes. We learn with a strong oxidant, primary alkyls can go straight to carboxylic acid. From ethanol we can go to what? Acetic acid. And from propanol, in this case, you can go to propanoic acid. Right? From hydrolysis of nitriles. From hydrolysis of nitriles, you can get carboxylic acids. Right? From carboxylation of Grignard reagent, keep in mind those two reactions for preparation of carboxylic acids. In this case, you are going to form a carboxylic acid. Right? The difference between these two, we are going to learn that in the next video, because nitriles are formed due to SN2 mechanism. And if you're going to synthesize a bulky carboxylic acid, it's not possible with nitriles. You are going to use carboxylation from Grignard reagent. Anyway, let's move to the reaction of carboxylic acids. The first one that we have seen, that is the reduction to yield what? To yield primary alkyls. Right? And with sodium hydroxide you can form carboxylate salt. It has also alpha substitution or nucleophilic acid substitution, but these are going to be explained in a separate video in the future. For now, that's it, and look forward to see you to the preparation and the reaction of nitriles. And there we are going to see 3 examples that include nitriles, carboxylic acids, and some other previous knowledge that we have get up until now. Up until there, peace.